Hi class, welcome to our new unit. This is all about functions, polynomials and graphing. And just keep an eye out as we go through this unit that we'll be chopping and changing from chapter 7 to chapter 10. So make sure you take notice of the name of the exercise because there could be some variance between the old book and the new book. So particularly if you're using the old book, really read the name of the exercise first. And this unit will be starting off with exercise 7H, functions. And your examples and pre-learning in this lesson will be example 18, using function notation. And your pre-learning for this example will be questions 1 and 2 in the new book and questions 5, 6 and 7 in the old book. And then there's example 19, which is recognizing a function. And your pre-learning for this example will be questions 3 and 4 in the new book and questions 2 and 4 in the old book. And then we'll do example 20, determining domain and range. And your pre-learning for this example will be 7 and 8 in the new book and questions 8 in the old book. The numbers for your pre-learning questions might give it away, but the order of the examples are different in the old book. You'll have to pay attention as we go along. Alright, I'll see you in the introduction. We've already seen relationships between two variables, and we will many more times this year. We've seen it in things like algebra, with expressions like y plus x equals 2, or y minus x squared plus 2x equals 3, or even y equals the square root of x. We've used tables like this one with x values of -2, -1, 0 and 1, and matching y values of 4, 5, 2 and 7. And let me close off that table. And tables can create sets of ordered pairs. So this table has one pair of -2, 4, as well as -1, 5 and 0, 2 and 1, 7. And if we collect them together in a set, we can call that set A. Of course, a set could have any collection of ordered pairs. They don't have to follow a discernible pattern. So -2, 4, -1, 5, -1, 2, and 1, 3 are a group of points, which together can form a legitimate set of ordered pairs, which I'll call B. We can also describe a relationship between variables by using graphs, which I'm going to draw on these axes. So here's a graph of a circle, here's one of a linear relation, and a quadratic relation. They are all an infinite collection of points, and each point has an x and a y value which relates to the value on the corresponding axes. These graphs, sets and tables, and algebraic expressions are all what we define as relations. In other words, a relationship between the x and y. So normally we think of x as the input and y as the output. So we can examine that with that set that we called A. Now it has x values -1, 1, 0 and 1, and y values of 4, 5, 2 and 3. And what those ordered pairs state is that the input value of -2 goes to 4, and when you read the other points we've also got -1 to 5, 0 to 2 and 1 to 3. Now you notice that each input has just one output there. Alright, so let's have a look at the other set B. So it's got the x values of -2, -1, that's also a -1, so it's still just -1 and 1. And it's got the y values of 4, 5, 2 and 3. And our first ordered pair has -2 going to 4, and then the next one has -1 going to 5, and then we've got -1 also going to 2, and 1 to 3. Do you notice here that -1 has two possible outputs? Well, the focus of today is about a special type of relation called a function. And the definition of a function is, for every possible input, there's exactly one unique output. So that would mean the set A is a function and B is not a function. But what about the set C that has the values -2, 4, -1, 4, 0, 2 and 1, 3. It has x values -2, -1, 0 and 1, And the y values here are 4 and also 4, so we just write that once, 2 and 3. And we could see that -2 and -1 both go to 4, and 0 goes to 2 and 1 goes to 3. So is this a function? Well, we need to go back to the definition, and that was that each input has one unique output. And we can see that the inputs -1 and -2 have the same output. So we're still asking, is it a function? But despite them having the same output, there is exactly one unique output for -2, and that's 4. And there's one unique output for -1, and that's also 4. So we have a unique output for each input. So this makes C a function. Now, functions have a very well-defined notation, for which we have the mathematical convention that x is the input, and for the function f, we write f of x. So I like to imagine x going into this function machine, and out shoots f of x, or the output. And as you heard me just say, we describe it as f of x. And the reason why a relation is not a function, if there's any uncertainty about the output, is that we like to think of them as machines. And in fact, they actually are the machines of mathematics. So, for example, we could have f of x is equal to 2x plus 3. The beauty about this notation is you don't need to write when x equals whatever. If I was to say when x is 2, in this case, we just write f of 2. So you can see I've got the 2 in place of the x in the brackets. So that means that the 2 takes the place of x inside that equation. So we started off with some algebra there. F of x is equal to 2x plus 3. But in this case, f of 2 is equal to 7. And if you're thinking about the x and y output boxes I had before, that means that 2 has the output of 7. And anything that has one output for each input can be written as a function, right? So we could have f of x equals to 3 to the power of x. And again, instead of saying when x equals 3, I'm just going to write f of 3 equals 3 to the power of 3, which equals 27. Okay, so the 3 is just taking the place of the x there. And in our arrow notation before, we would say that 3 goes to 27. Now, when graphing functions, like one we've already seen this year, f of x equals x squared minus 1. Well, you've seen f of x as y, right? Well, that actually gives the hint of what I'm trying to say now. If I'm going to make out my axes y and x, then we've got our x-axis here, and I'll put the x in now. And of course, this is our y-axis, and that parabola looks something like this, doesn't it? Whatever point we see on this graph now, it's going to have an x value of, say, a, and its y value is f of a. So I know when x is 1, f of x equals 0 there. But I can still express it as f of 1, okay? And the way to look at these graphs, of course, is that y equals f of x. And when we graph relations, we're able to check if that graph is a function. And that's because, as our definition says, each input has exactly one output. So that means that every vertical line could only intersect with the graph of a function once, because each vertical line represents all the possible y values associated with that x value. And with x being the input, if that x value has more than one output, then it's not a function, right? So let's have a look at y equals x squared. Sorry, I mean square root of x. So if I'm going to graph that on these axes, because the square root of 4 is equal to plus or minus 2, of course there's going to be no negative values of x square rooted, but each x value has a positive and a negative value, right? And our graph would look something like this if I mark in the x and y. So let's mark in where 4 will be, around about. And I've added a horizontal line there. So you can imagine this point here would be 4, 2, okay? But also the square root of 4 is minus 2 as well. So this is definitely not a function. And that's sort of why we focus on the positive values of square roots, by the way, but that's another story for another day. So now if a graph fails a vertical line test, that means there's more than one output for that x, so it is not a function. And it's also important to realize that if the vertical line test fails for just one value of all the possible inputs, then that relation created by the graph is not a function. And there's one more important topic to cover today, and that is domain and range. So the domain is the formal name for the set of all the possible inputs. And the range is the formal name for the set of all the possible outputs. So for example, our set A has a domain of -2, -1, 0 and 1, and a range of 4, 5, 2 and 3. And for an algebra thing, so for example, y equals x, i.e. f of x equals x, the domain is all possible real numbers. There's no number that can't be put into this function because it just is them. And the range is all possible real numbers. And that's because whatever number you wanted to get out, you just have to put it in, right? We get out what we put in. And don't be confused, the list of objects in curly brackets or a statement like all possible real numbers are both sets. We just state this one in a sentence. You're going to be there for a long time if you try and write out all the real numbers, right? Now you can also look at domain and range for a graph. So let me draw a circle here. Perfect circle, right? So let me give the left and right of the circle values A and B. So yeah, obviously then all x values are between A and B. I'm going to call these values C and D. So all the y values are between C and D. So the formal way of saying between A and B is saying that the domain is A less than X, which is less than B. And obviously the range is C is less than Y, which is less than D. So they're the key ideas for today. Some of you might find this straightforward. Have a look and see if you need to do the building and understanding questions, which are questions 1, 2 and 3 in the old book. Alright, so let's get on to the next section. For a function f of x, what that's really saying is do stuff to any x that you can do stuff to. So that means if I have another number a, then f of a is do that stuff to that a. So for example, if f of x equals 3 times x plus 2, then the stuff you got to do this time is multiply your input by 3 and add 2. So that would mean if I had f of 2, then we have 3 times 2 plus 2, which is equal to 6. I also want to note that you've used this sort of thing before with objects like sine of x and log of x. Alright, let's get on to example 18, where for the function f of x equals x squared minus 3x plus 1, we're going to find the following. Part A, we're going to find f of 0. So subbing 0 in, we've got 0 squared minus 3 times 0 plus 1, which equals 1. Okay, hopefully you know your 0 squared. Alright, part B, we've got f of minus 3. So that means we have minus 3 squared minus 3 times minus 3 plus 1. So minus 3 squared is 9, minus 3 times minus 3 is plus 9, plus 1 is equal to 19. And finally part C, we've got f of c. Well, we just have to sub in c for x, so that means we've got c squared minus 3 times c plus 1. And the brackets here are really superfluous, so let's just write c squared minus 3c plus 1. Okay, so that's to make a point that it doesn't have to be a number that goes in there. You can have a simple algebraic term like this, or you could even put a fairly complex one in there, such as c squared minus b on 2 or something. I also want to note that you might have noticed me use these brackets like this with these sorts of equations all year already. And that's because I obviously studied functions many years ago, and it does make things a lot less complicated if you start off with brackets for your input like that. Okay, so that's it for this section. Pause your video now and do questions 1 and 2 in the new book, or questions 5, 6 and 7 if you have the old book. And then we'll see you in the next section. When you have a set or collection of ordered pairs, i.e. A and B, or an equation such as y equals stuff with x, or a graph, then it is a function if for each possible input there is only one possible output. So for ordered pairs, you're going to need to check each input. And the convention is for AB, A is the input and B is the output. And then for equations, the convention is stuff to y equals stuff to x, and our y is the output and the x is the input. Often there's some algebra and reasoning involved. I'll give you a hint. If you see y squared, it's not likely that it's a function. And for graphs, where points are marked like ordered pairs, A, B, and A represents where it relates to the x-axis, and B relates to the y-axis, then the convention is x is the input and y is the output. And for these graphs, you should use the vertical line test. Because if a vertical line intersects a graph more than once, then there are more than one possible outputs for that value of x. Alright, let's move on to example 19, where we'll be identifying which of the following are functions. So in part A, we've got a set of ordered pairs, 1, 4, and 2, 8, and 4, 16, and 5, 20. So we can see that the x values are 1, 2, 4, and 5. And the y values are 4, 8, 16, and 20. And 1 goes to 4, 2 goes to 8, 4 goes to 16, and 5 goes to 20. So each input there has just one output, therefore this is a function. Alright, let's have a go at part B now. We've got an equation, y equals x squared plus 3. There's only one possible output for each x. Okay, so even though there might be more than one x equal to the same y, so for example, when x is equal to 1 or minus 1, it's the same. But the point is, when you put x into this equation, you know what y is going to be. There's only one possible outcome. Alright, so because of all that, this is definitely a function. Alright, finally, part C, we've got a graph of a circle. And this is a unit circle, so everything is 1 or minus 1. Now if I use the vertical line test for the graph, just picking out this x value here, you can see that we're going to have two intersections. So therefore for that value of x, there are two values of y associated with it. So this means that the unit circle is definitely not a function. So that's an example of all three types of situations that we're going to be looking through. So right now you should pause that video and do questions 3 and 4 in the new book, or questions 2 and 4 in the old book. And then we'll see you in the next section. With regards to functions, the domain is all possible inputs and the range is all possible outputs. So the way I like to think about it is, if we have a function machine, f of x, then our domain is anything that could fit in there, and the range is what it shoots out. Sometimes figuring this out is really obvious, other times you're going to need to use a bit of reasoning and maybe even a bit of algebra. Alright, let's move on to example 20, where we're going to determine the range and the domain for the following functions. Part A, we've got y equals 4x minus 1. So for this function, when we're considering the domain, you're able to multiply any real number by 4 and then minus 1 from it. And regards the range, 4x minus 1 is a line, so that should be clear enough to you already that we'll be able to get any y value we want, right? But if you want to do some formal algebra with that, what you could say is if y was equal to a for any real number, and if a is equal to 4x minus 1, then to solve that for x, I'm just going to add 1 to both sides and then divide it by 4. And what that means is, for this a, I can find any x to produce the a using the formula. In other words, I'm just going to add 1, then divide it by 4, and whatever that x is, I can get this a. So anyhow, the formal answer is, for y equals 4x minus 1, the domain is any real number value of x, and also the range is any real number value of y. And if you know the answer and don't want to do all the algebra I did earlier, you can write that out. Alright, part B, we've got y equals x squared minus 4. And once again, when thinking about the domain, you're able to multiply any real number by itself and then subtract 4. So that's fine. But for the range, we're going to do a bit more thinking. And because 0 times 0 is 0, and a times a is a squared, and minus a times minus a is also a squared, this means that whatever x we have, x squared is going to be greater than 0. Well, greater than or equal to 0. So if I subtract 4 from both sides, then we have x squared minus 4 is always going to be greater than 0 minus 4. Or in other words, x squared minus 4 is always going to be greater than or equal to minus 4. And x squared minus 4 is a definition of y. So that means that y has to be greater than or equal to minus 4 as well. So this is an answer you're going to have to take note of, okay? Because you can see how I have tried to build up y with how I represent it with x, and that's what's allowed me to establish what the range of this function is. Alright, let's write out the formal answer. For y equals x squared minus 4, the domain is any real number x, and the range is any real number y where y is greater than minus 4. Also, please take note that we could still define the domain and range with relations. And of course, the domain is all the possible x values, or where it covers the horizontal axis, or the first of all ordered pairs. And no surprises that means that the range is the y value, or where it covers the vertical axis, or the second of an ordered pair. Alright, let's get on and do that example. So pause your video and do questions 7 and 8 in the new book, or question 8 in the old book. And then when you come back, we'll be able to summarize this lesson. This unit will see us work with many functions and relations. And thinking about them as functions where appropriate will help you with a lot of your algebra. Also, thinking about the domain and range will help you think about graphing and some of the concepts behind the graphs. And generally speaking, functions or relations are the second most important thing in maths after sets. So make sure you keep that in mind for every maths class you do from now on. So the way I like to think about it is the sets are the universe and all the stuff in it, and functions are the forces. Alright, so in this class, a successful student will understand what defines a mathematical relation and function, know how to recognize or test for a function, be able to use the standard notation for functions, know the meaning of domain and range of a function, and be able to find the set of allowable x values, i.e. the domain, and resulting y values, the range of a function. So there you go, this lesson does seem to have more ideas than work. So spend some good time thinking, alright? Okay, I'll see you in that next class, be that in the classroom or in the video. Bye.